The first step to becoming a master of curved arrows is really mastering the bookkeeping aspect of the curved arrow formalism. And so let's practice with this using a couple of examples. The first skill you're going to need to have is the ability to draw products implied by a given set of curved arrows and reactant structures. So here, for example, we have water and this cationic species here. This carbon just has the three R groups indicated, no implied hydrogens. And so what we can see from the given curved arrow is that the source is here, and the electron sink is this carbon atom. That's where the given curved arrow is landing. What is the arrow telling us? Well, the oxygen in H2O has one lone pair that's done nothing. The lone pair acting as the source has formed a new bond to the sink carbon, which I'll just briefly highlight in blue here. The three R groups attached to the carbon serving as the electron sink are still there and haven't done anything. And so this is our final structure. The only thing we haven't accounted for are changes in formal charge. The source has increased in charge by 1 unit. And if you'd rather not think about this at that level, just look at the structure of the oxygen atom in the resulting product. It has a formal electron count of 5, 2 from this lone pair, 2 from each of the OH bonds to hydrogen, and 1 from the new carbon-oxygen bond. That count of 5 indicates that the formal charge on this atom is +1. The carbon atom that served as the sink is now neutral. It's a plain tetrahedral carbon with 4 bonds to atoms. So notice here again that the electron source, the oxygen atom in this case, has increased in charge by 1 unit, and the electron sink, the carbon atom here, has decreased in charge by 1 unit. You'll also want to develop the ability to draw curved arrows based on the structures of given reactants and products for an elementary step. This will help you recognize patterns in reactivity, the common types of elementary steps that we see in organic reactions. And if you go out and study reactions on the web or from a source other than your textbook, you'll actually commonly see errors in given curved arrows. So being able to do this helps you apply the curved arrow formalism rigorously so that you're as successful as you can be on exams, for example. In doing this, recognizing implied hydrogen atoms and lone pairs is often a key skill. So for example, in this reaction shown here, there is a hydrogen shown here that appears not to be present on the corresponding atom in the starting material. Of course, if we think about this for a couple of seconds, we'll realize that based on the conventions of the shorthand, there is a hydrogen atom here. This hydrogen is present so that that carbon satisfies the octet rule, and so this hydrogen doesn't really participate in the reaction shown here. I recommend numbering the atoms involved in the reaction. We also call this mapping the atoms in the reactants onto atoms in the products. And we'll do that with the 3 key atoms involved in this reaction: the carbon, the nitrogen atom, and the oxygen atom that goes from being doubly bound to singly bound in the product. It's probably also worthwhile to note that this atom that goes from neutral to positively charged is also involved to a degree in the reaction. Now that we've done this, we can start highlighting bonds made and broken. What we can see among the bonds broken is that the bond between nitrogen and oxygen, nitrogen 2 and oxygen 3, is broken. So I'm going to go ahead and highlight that in the reactant. Since it's broken, it participates in the curved arrows and electron flow in that sense. And we see that the bond between carbon 1 and carbon 4 is also broken, since we have a double bond there in the reactants, but no double bond exists there in the products. Among the bonds made, we find that a new bond has been made between carbon 1 and nitrogen 2, and we find that a new lone pair has appeared on this oxygen that's now formally negative. From these observations, we can conclude that the electron flow must begin between carbons 1 and 4. This is the electron source. Notice that carbon 4 goes from neutral to positively charged. Its charge increases by 1 unit. So the first curved arrow will show the use of those double bond or pi electrons to form a bond to nitrogen. And the second curved arrow has to show the cleavage of the NO bond and the appearance of this new lone pair on oxygen 3. And so that arrow is going to look something like this. We're going to take the double bond electrons in the NO double bond and give them to oxygen like so. And now we've reached a situation where the curved arrows we've drawn imply these products. There are really 3 key skills built into this process. The first is identifying implied hydrogens and lone pairs. And this is easy to skip over. You'll see people sometimes skip this step, but it's essential, in my opinion, when you're first starting out. The second key skill here is mapping atoms in the reactants and products. And the idea is this prepares us for the next step, which is identifying bonds made and broken, and especially focusing on the pairs of electrons associated with those bonds made and broken and what their fate is over the course of the elementary step. Only after these three first steps are done, then we start drawing curved arrows. This is a situation where, at least in the beginning of applying the curved arrow formalism, you want to apply that detailed, rigorous analysis so that you really understand the bookkeeping of the system inside and out.